So my name is Mary Dickinson. I am the Regional Sustainable Design Leader at Perkins & Will. That is a global architecture and design firm, so very different maybe from some of the other moderators that you've had up, and hopefully we'll have a pretty interactive discussion today based on that. A little bit about my background. I work a lot in sustainability, but I have my degree in interior design, and that correlated to sustainability because I started to think about what could my impacts be on occupants, on their health, in the way that I design, in the way that I think about the environment. And the more and more I got into sustainability, we heard a little bit from Mahesh earlier, we really start to think about materials and the material makeup, right? So the other hat that I wear within the firm is that I'm co-director of the Material Performance Lab. And my lab basically wants to look at what are the impacts of what we do on the health of occupants and on the health of the environment. I manage the firm's precautionary list, which is a list of substances that we find in building materials that have known or suspected human and environmental health impacts. And the way that we go about that right now is on the hazard approach. If there is a known or suspected hazard that has been provided by the scientific community, yourselves, or a governmental body, we look at those and we see how often those show up in building materials. We worked with Gina's group, the Healthy Building Network, to assess how many times did these substances show up in building materials, and then made a decision as to what needed to show up on that list and go after the heavy hitters that really appeared over and over and over again. So that list is really important to us, and your work is extremely important to us because it lets us know in the design community how we can make change, impact change, to make these healthier spaces. In addition to that, this community is looking at indoor studies. What is the pre and post occupancy impact of those decisions? And we want to see what other substances are showing up that we're not thinking about. There's been a little bit shared already about all of these chemicals and the compounds that are created on a daily basis, and what do we or do we not know? And so that's really important to us in these studies to try to find out. So I'm really excited about today's panel and how this correlates into what these fine doctors have been studying. We're looking at indoor chemistry problems and solutions. And I think we'll have a lot to talk about. So I want to introduce each of our speakers and then have them come up, and then we're going to change it up a little bit. We're going to have a transition question in between to kind of get some thoughts going. So first off, we have Dr. Manabu Shiraiwa, am I good? Who is an associate professor of chemistry at the University of California, Irvine. Dr. Shiraiwa serves as the principal investigator of the Modeling Consortium for Chemistry of Indoor Environments. The project that he's been working on has a goal to develop comprehensive integrated physical chemical models that include a detailed representation of the chemistry in the indoor environment, whether on the surface of materials, as particles, as a gas, and then to simulate how occupants, their indoor activities, and buildings influence those chemical processes. What I really liked that he shared with me earlier when we were talking, he said, I never thought I was going to be talking to an architect, an engineer, or a designer, much less. And this is really exciting to him, so I'm happy for that. So Dr. Shiraiwa, if you'd like to come up. Take us away.
Okay. Thank you for nice introduction, and thanks to AAAS, Annette, and Paula for organizing this great symposium and having me here. And I'm gonna introduce you about our modeling projects. So I'm a chemist and a modeler, so I'm gonna talk about our activities on indoor chemistry. So the Modeling Consortium for Chemistry of Indoor Environments is funded by Sloan Foundation. So we are trying to model indoor chemical processes, including surface interactions, pollutant dynamics, and chemistry happening in the gas phase, and also the formation of secondary organic aerosols. And we are the team of 8 investigators from 7 different institutions and 3 postdocs and 7 students. And the unique thing of this consortium is we cover the wide range of time scale and length scale. So we have Professor Doug Tobias from UCI, who does molecular dynamic simulation, who is dealing with less than 1 nanosecond and molecules. And myself working on kinetic process model with Glenn Morrison on kinetic processes happening on skin, clothing, and indoor surfaces. We have co-PI Nick Castro from University of York, who does gas-phase chemistry modeling, and Michael Waring from Drexel University on modeling secondary organic aerosol formation in indoor environments, and Dong-Hyun Lim, who works on computational fluid dynamics, who is dealing with scale of days and room scale, basically. We have 2 new investigators recently, John Little from Virginia Tech and Andy Zuent, who does thermodynamic modeling. So the aim of this consortium is really to work together and connect different scales of models. And you will, of course, question, how come you connect molecular dynamic simulation with CFD? But we actually made it happen. These 2 people have now co-author papers. And I want to show today that how we really bridge the scale. The strategy we have is of course difficult to directly connect MD simulations with CFD, but he can climb up using me as a stepstone, right? Climb up. I'm going to show how we do that, how we did it. Okay, so what are our objectives? So the objective is to develop, at least this is our ambition, to develop comprehensive integrated indoor chemistry models, it's chemistry models, okay, that include a realistic representation of gas, aerosols, and surface chemistry. So that's the big objectives we have. And then another big point is we want to integrate with experiments and measurements. So we want to assess gap in our fundamental understanding of indoor chemistry, and we have a focus points of 2 points. One is the role of occupants and also the impact of indoor activities, and we focus on the cleaning. To do that, why we want to do that is we want to generalize observations, because often experiments or measurements are conducted at certain conditions or even high concentration, and to generalize that, maybe you can use a model to achieve really predictive capability. So the point is also we want to make predictions, right? So that's our goal and ambition, to make it, to develop a model, integrate with experiments, measurements, and to gain the predictive capability. So why MOCCIE, why we exist, and why experimentalists or measurement people think about collaborating with us? I have 2 important points for you. So the first point is by working with us, you could gain mechanistic and quantitative interpretation, namely testing hypotheses. So you do experiments, you have measurements, you have some observations, you may have some hypothesis, you want to test it, and we can help doing that. And I will show you with these 2 studies how we do that in this talk. The second point is you can extrapolate to different indoor conditions and also even inaccessible properties by measurements. Okay, so often experiments, particularly lab experiments, are conducted often at high concentrations so that you can see the signal. But in real indoor environments, maybe concentrations are low, reaction times can be longer. Using the model, you can extrapolate to different conditions. And also, another point is inaccessible properties. For example, you may measure average ozone concentration in the room, but you may not know how ozone is distributed in the room. And using CFD, you can address such questions. Okay, with this point, I'd like to show the first study, which is looking into the ozone reactions with humans. So in this morning, Jonathan Williams gave a wonderful talk on that, and we are modeling such processes. Okay, we look into reaction of ozone with clothing and skin, and Doug Tobias can do a molecular dynamic simulations. Now this red dot is ozone molecule flying into the skin oil. He can calculate Henry's law constant, bulk diffusion coefficient, how ozone interacts with your skin. Using that information, here's my postdoc, Pascal Reiki, constructed a kinetic model which can treat how ozone interacts with clothing. It may diffuse through clothing, reach skin, it reacts with squalene, which is a skin oil component, and then generate such SVOCs into the gas phase. So we have a kinetic model to simulate such processes with a multi-layer method we developed. And using that kinetic model information, we feed that information to computational fluid dynamics run by Dong-Hyun Lim. So with that, MD and CFD is indirectly connected through kinetic model. So by achieving such models and model framework, we can simulate experiments. This is experiments, the benchmark experiments conducted by Charlie Wechsler and Ami Wisthara, published in PNAS 2010, that in time 0, 2 people enter the room and ozone concentration goes down. This is the measurements, markers of measurements, and we can model that using our model, reproduce it. And at the same time, these SPOCs are generated by humans. So this is 6-MHO and 4-OPA is generated, and we can use our model to explain this data. So the model is these lines, and we can reproduce these measurements. And the point is some of these compounds, particularly carbonic compounds, are known as respiratory or skin irritants. So now we have MD simulations feeding into kinetic model that is constrained to the measurements, then connect with computational fluid dynamics. This figure shows the spatial distribution of semi-volatiles. This one is 6-MHO primary product of reaction. 4-OPA is a secondary product. And with such exercise and modeling studies, we show that soil clothing protects skin from ozone exposure, but it can enhance exposure to oxidation products. And you can see about 1.6 to 2 times higher concentrations in the breathing zone than in room air. Okay, so put this in the context of real life, following this plenary speaker, that so we sometimes are very busy, too busy to laundry, right? But better do laundry, right? And some people are even proud of wearing same clothing every day, like scientists or students. But you may really want to wash your clothes because the soil clothing, you would pollute yourself, okay? Not only pollute yourself, but also pollute your colleague. So that's one of the insight you can get from modeling that, okay, let's do laundry. We are busy, but we should still do that. Okay. All right, so I wanted to move on to the next study in collaboration with Vicky Gracian, she's sitting here from UC San Diego. So there's SVOCs and VOCs in indoor environments. We had a great talk with Alan Goldstein, and we want to understand how that interact with indoor surfaces. And Vicky Gracian's group conducted experiments how it absorbs on the glass surfaces, SiO2. So she did measurements. And then now, again, molecular dynamic simulations by Dr. Tobias, he can tell how exactly molecules interact with surfaces. And that information can be fed into our kinetic model to explain the adsorption and desorption kinetics. So again, the state-of-the-art experiments, molecular dynamic simulations, kinetic model, we can explain and then get some critical information such as adsorption enthalpy of the Limonene adsorption onto SiO2. For the next study, we looked into the reaction of ozone with polycyclic aromatic hydrocarbon in oil films. So this is in collaboration with John Abbott from University of Toronto. So the motivation of this study is that if you do cooking, such as stir fry, particularly using oils, namely Chinese cooking, you use lots of oils, and incomplete combustion would maybe probably lead to the formation of oil films in kitchen particularly, that would mix a mixed film, which is polycyclic aromatic hydrocarbons, which is actually carcinogen and toxic, embedded into cooking oil. And he did experiments exposing this film to ozone, and they measure how fast this PAH would decay away. Okay, and then this is his experimental data. I don't want to go into too much in chemistry, but what we found is actually during this course of reaction, phase separation and slow diffusion really prolong the lifetime of PAH in indoor surface films, and we extrapolate to different indoor conditions, namely lower ozone concentration, and really show that the effect of this detailed physical-chemical processes, namely phase separation and bulk diffusion, can impact the lifetime of PAH in indoor surfaces. Okay, then at last, I want to show that Nina Barnes gave a fantastic talk this morning about home chem. So we are also modeling that process. And I show one example here, particularly interacting with Delphine Farmer and home chem team, that they did breach cleaning, and then they found ammonia concentration drops, and then these kind of chlorinated compounds is formed and decayed away. Okay, and then to simulate such breach cleaning processes, we constructed a model that considers gas phase reactions, surface reactions on the surface, particle uptake, photolysis reaction, and so on, and also chemistry in breach layer. So with this chemical reactions, which is happening on the indoor surfaces, we can reproduce their measurements. So by doing that, so this was Delphine Farmer has a hypothesis, probably multiphase chemistry is playing a role, and we tested that hypothesis by implementing that model, by implementing that reactions into our model. So with that, I want to leave you with 3 take-home messages. So first message is MOCCIE, MOCCIE team, modeling team collaborates to combine models, particularly with different scales of models, and aiming to develop integrated indoor chemistry models. MOCCIE integrates with experiments, measurements to gain fundamental understanding of indoor chemistry. And MOCCIE predicts, at least this is our ambition, we are maybe not fully there yet, but we want to quantify and predict impacts of indoor activities and chemistry at humans and surfaces. And then really our ambition and the big goal is to help achieving healthy indoor environments. With that, thank you very much.
For a minute. Okay, so the question that I have for you, since we're kind of talking about this interdisciplinary work, right, and thought processes, based on what you've been working on in the modeling, how do you foresee your modeling software changing how designers or engineers can change how they might design the mechanical systems or change the mechanical systems based on what you've learned so far?
Yes, so that's a very important question, and I don't have a single answer because maybe answer could be different depending on the different conditions. But in terms of human exposure, particularly to SVOCs, probably that higher exchange rate will be desired, but this depends on the condition because if outdoor is really polluted, you don't want to bring polluted outdoor to indoor, right? And so there's trade-off, but yeah.
We need to work together.
Yes, I know. That'll be great.